Hello friends, I am Prof.Darshan Thakur from Terna Engg.College, Usmanabad. Welcome you on my YouTube channel Control System Engineering. As far as today's session is concerned, so we will try to learn certain basic things regarding to the mathematical modeling of control system, right? So let us quickly go through. The objective for our today's session is to what? So as you can see, such type of mechanical system we are having with us, and our objectives are nothing but what? First of all, we need to determine the system equation, and second one is nothing but what? We are supposed to draw the force voltage analogous circuit or the force voltage analogous network, right? So first of all, we need to understand modeling is nothing but what? Modeling is nothing but the way in which we are representing this given control system, or more specifically mechanical system, in terms of certain system equation, right? So in order to write the system equation, first of all we need to understand the basic components of this mechanical system. So as you can see, there are three basic components of this given control system that can be categorized as a mechanical system. So these three components are nothing but this M stands for mass, right? This K stands for spring, and this B stands for damper, or we can call it as a forcing element, right? So as you can see, first of all we need to observe how many number of elements we are having with us in this given mechanical system. Along with these elements, F stands for what? This is the direction of force. The force is being applied with respect to this ground axis or the reference axis, right? So whenever such type of force is being applied to that mass or to that particular body, so as we are very much aware of this thing, all the particles belongs to that mass or belongs to that body will go through the equal displacement. That is to be denoted by this x1 and x2, right? So there are three basic components. M stands for what? Mass, K stands for spring, and this B stands for damper, right? So this mass is nothing but what? As I told you earlier, there will be the process of acceleration through that mass when we apply a certain force. So this mass, it is denoted, or it is equivalent to the acceleration. Means what? In case of algebraic language, acceleration is nothing but what? The second order differentiation, right? So how to represent this mass? M followed by d square x upon dt square. This is the system equation for that mass. Similarly, K, that is nothing but what? Spring. So to that spring, always we are having these two ends, A and B. If we apply that force from left hand side to the right hand side, so the net displacement will be what? A minus B. If we apply the desired force from right hand side to the left hand side, so the net displacement will be B minus of A, right? So its system equation will become K into X, right? K is nothing but what? The proportionality constant for that spring. And damper, right? Damper, as far as this mechanical system is concerned, so purely it deals with this terminology that can be called as a motion. So either it is translation motion or the linear motion. So the parameter which will try to oppose the flow of motion is nothing but what? Damper, right? So damper is equivalent to the velocity. So its system equation will become what? D into dx by dt, where x is nothing but what? The desired displacement taken by that damper, that spring, or that particular mass, right? So these three are the important components, right? So in order to achieve, the first objective is what? Obtain the system equation, right? So for that purpose we need to convert this given mechanical system into its equivalent nodal diagram in that first step. Once we are having the nodal diagram, then we can write the system equation for that given control system, right? So in that first step, what we need to do, here I will write. In that first step, we need to draw the nodal diagram, right? So nodal diagram means finite number of nodes we are having with us. Nodes, in case of network engineering, it is a part at which multiple number of branches are interconnected to each other. That is nothing but our node. So first of all, we need to determine how many number of nodes we need to complete its nodal diagram. So always we need to remember that number of nodes equals to number of displacement, right? That we need to understand, plus 1. So this is the desired statement for a nodal diagram. Number of nodes equals to number of displacement plus 1. This additive 1 is for our reference axis or the ground axis, right? So usually number of nodes equals to number of displacements. Number of displacements equals to number of mass. To that mass we are having a certain displacement with respect to this force, right? So m1 is associated with this x1, M2 is associated with this X2. What about this K1 and B1? Clearly we can say that the lower leg of this K1 and B1 are associated with this X2, and the upper leg of this K1 and B1 are associated with this X1, means these two components are connected in between X1 and X2, right? Similarly, as far as the remaining two components are concerned, K2 and B2, how these two components are connected? The upper leg of this K2 and B2 are terminated at reference axis, and the lower leg of K2 and B2 are associated with this displacement number 2, means these two components are connected in between ground axis and the displacement number 2. That we need to understand how these components are associated with these two, displacement and the reference axis, right? So here first of all what we need to do, we need to draw the nodal diagram. So as I told you earlier, number of nodes equals to number of displacements. So right, so this will be the first node denoted by x1, and this will be the second node denoted by displacement number 2, right? So, and this horizontal axis stands for what? The reference axis or the ground axis, right? So as you can see, the direction of force, this is, that arrow indicates what? In that direction that desired force is being applied. So obviously there will be a certain displacement taken through that M1 as well as M2, right, which will occurs in the direction of applied force, right? So first of all we need to indicate how this M1 and M2 are connected in this nodal diagram, right? So this M1 is associated with this reference axis and the displacement number 1 as a result of force applied, right? So how this M1 is connected? In this way, it is connected in between displacement number 1 and the reference axis, that is nothing but what? M1. Similarly, this M2 is connected, it is connected in between reference axis and the displacement number 2, right? Now see, this F is nothing but what? The most important factor for we people, the direction of F indicate the direction of force, right? The direction of force is towards the displacement x1 as well as x2. Then immediately after that we need to decide how these two intermediate components are connected, K1 and B1. So as I told you earlier, K1 and B1 are connected in between x1 and x2, right? So here we need to show in this way. See, this will be the K1 and this will be the B1. That is nothing but x2, right? So this is K1 and this is B1. This K1 is connected in between x1 and x2. B1 is also connected in between x1 and x2, right? What about this M2? M2 is associated with this reference axis and the displacement number 2. Now the remaining components are nothing but what? The spring number 2 and the damper number 2. So how these two components are connected? These two components are connected in between reference axis and the displacement number 2. So in that way we need to show here, this is nothing but what? K2, and this is nothing but what? B2. Right? So this is how the nodal diagram is being completed. Then after that what we need to do? Here we need to assign the direction of force belongs to each and every branch, right? As far as this node number 1 is concerned, so obviously this is the direction of force which is incoming towards that node. So obviously as far as this M1, B1 and K1 are concerned, so the direction of force belongs to M1, B1 and K1 are outgoing from this x1, right? The direction of force belongs to M1 is outgoing, the direction of force belongs to K1 and B1 are outgoing from x1 towards the x2, right? Now after that what we need to do? We need to apply the strategy whose name is nothing but what? KCL, Kirchhoff current law, right? So as we are very much aware of this thing, Kirchhoff current law says that sum of incoming plus outgoing currents equals to 0, or sum of incoming currents equals to sum of outgoing currents. Here we need to use this KCL strategy in terms of force terminology, right? So the sum of incoming force equals to sum of outgoing forces, right? So when we apply this KCL strategy in terms of force at this node number 1, so we are coming on this conclusion that at node number 1 there are how many branches? There are 4 branches, 1, 2, 3, 4. Out of that 4 branches, 4 branches. The direction of force belongs to this F is incoming. Remaining branches force are the direction of force belongs to remaining branches is outgoing, right? So accordingly, the KCL equation will become what? Here I will write. Here F equals to, now the system equation for mass, how that mass is being mapped in terms of system equation. Mass stands for acceleration, means second order differentiation. Damper stands for first order differentiation, and spring means what? Net displacement from right hand side to the left hand or from left hand side to the right hand side. So by taking into account this fact, the system equation will become what? M1 into d square x1 upon dt square plus d1 into dx1 by dt plus k1 into, sorry, as far as this damper number 1 is concerned, how it is connected? Damper number 1 is connected in between x1 and x2. So the net displacement will be what? x1 minus x2. So with respect to this first order differentiation, d by dt, it will become x1 minus x2 plus k1 into x1 minus x2. I will put this term within this parenthesis, right? Because these two parameters are connected in between node number 1 as well as node number 2, right? So similarly, this equation can be treated as a equation number 1. So when we apply this Kirchhoff current law at node number 2, so at that time, first of all we need to observe how many branches are connected at node number 2. So again at node number 2, 1, 2, 3, 4 and 5 branches are connected. Out of that 5 branches, the first 2 branches, those are already it is being considered in that node number 1 as a outgoing, right? So obviously it will become incoming to that node. The direction of these 2 branches are incoming at this x2, and the direction of remaining 3 branches we need to assume as a outgoing, right? So the sum of incoming current, sum of incoming forces equals to sum of outgoing forces, right? So the system equation at node number 2 will become what? It will become k1 into x1 minus of x2 plus b1 into d by dt x1 minus x2, right, equals to, right, because as far as this entire term is concerned, which is written to the left hand side of this assignment operator, this is the sum of incoming forces. Still we are having the 3 different branches, so we need to map these 3 branches in terms of their system equation. So it will become what? M2 followed by d square x2 upon dt square plus this k2 into x2 plus this b2 into d by dt x1 minus x2, right? So this is nothing but what? Equation number 2, right? Now I just hope that you are getting equation number and equation number 2. How we are getting these 2 equations? By applying KCL at node number 1 and at node number 2, right? So this is our first objective. These two represents the system equation for this given mechanical system, which are to be defined from this nodal diagram. How this nodal diagram is to be completed? Number of nodes equals to number of displacements. After that, how these elements are associated with this reference axis and these 2 displacements according to the direction of force, these are being connected in that nodal diagram, and from this nodal diagram these 2 system equations are to be defined. Then after that, our second objective is nothing but we are supposed to draw the force voltage analogous network. Analogous means what? Similarity. Analogy is nothing but what? How one element is similar to another. So for that purpose, what we need to do, I will remove this nodal diagram in order to complete our objective number 2, and I will keep these 2 statements on this board as it is, right? So force voltage analogous network, which we need to draw. So first of all, we need to recall what are the different analogous terms, right, in this mechanical system that we need to recall, right? So as its name indicate, it is the force voltage analogy. So this force is analogous to voltage, and what are the 3 important components of this mechanical system? This mass, damper and spring. So M is analogous to inductor L, right? damper, it is the basic property is to oppose the flow of current. So which electrical parameter is responsible to oppose the flow of current? That is nothing but what? Resistance. So B is analogous to R. K stands for what? Spring. It is denoted by this elasticity statement 1 over C, and this X is being, this X, that is nothing but what? Displacement, is analogous to charge. That is nothing but what? Q. Right? So we need to recall these analogous term, and what we need to do, we need to apply this analogy statement as well as Laplace transform to equation number 1 and equation number 2. Means further two equations we need to declare, and from these two equations we can draw the force voltage analogous network. To draw the force voltage analogous network, what we need to do, we need to apply the force voltage analogy as well as Laplace transform to this equation number 1. Right? So basically Laplace transform, it will convert time domain expression into frequency domain. So as a result of doing this, it will become F is analogous to V. So it will become, I will write V of S. Right? Here. So V of S equals to M is analogous to L. So if it is M1, then it will become L1. Right? As it is a second order differentiation, so which Laplace variable is being used? S square. So it will become S square. X is being replaced by Q. So it will become S square into Q1 of S plus B is analogous to R. Right? So B1, it will become R1. First order differentiation means which Laplace variable? Yes. X1, that will be replaced by Q1 of S minus Q2 of S plus remaining statement is what here? K is being replaced by elasticity 1 over C. Right? So 1 over C into X, that is nothing but what? Q1 of S minus Q2 of S. Right? So this is nothing but what? Equation number 3 by applying the force voltage analogy as well as Laplace transform. Right? So same thing is applied for this equation number 2, which is to be declared after applying Kirchhoff current law at node number 2. So as far as this equation number 2 is concerned, so we will start writing this equation with this K1. So this K is nothing but 1 over C. So it will become 1 over C into Q1 of S minus Q2 of S plus B is nothing but what? Damper is being denoted by R. So it will become R1, as it is a first order differentiation. So R1 S into Q1 of S minus Q2 of S equals to, again few three terms we need to write, those are being written to the right hand side of this assignment operator. This M is analogous to L, so it will become L2 into second order differentiation, so S square into Q2 of S plus K is nothing but what? 1 over C2 into Q2 of S plus B is nothing but what? R, first order differentiation S, that is nothing but what? B2 into, here which displacement we are having? Here only we are having, it is not x1 minus x2, B2 into dx2 by dt, because this damper number 2 is associated with this reference axis and the displacement number 2, so it will become R2S times of Q2 of S. This is nothing but what? Equation number 4. Now in this way we are getting equation number 3 and equation number 4 by applying force voltage analogy as well as Laplace transform. Now in order to draw the force voltage analogous circuit, now here I will remove this equation number 1 as well as 2. Now see, as far as we are having equation number 3 and equation number 4, so in these two equations we need to replace this term I of S equals to S into Q of S. So S into Q of S, according to the force voltage analogy, I of S equals to S into Q of S. So we need to replace this term S into Q of S with this I of S, right? As a result of replacement, one more time we need to rewrite this equation number 3 and equation number 4. So as a result of doing this, equation number 3 will become what? Here I will write equation number 3 V of S equals to S into Q of S is being replaced by I of S, so it will become L1, as we are having the S square, right? So it will become L1 times of S into I1 of S into I1 of S plus remaining term is what here? R, as it is. S into Q of S is nothing but I1 of S. So it is Q1 of S minus Q2 of S, which will become I1 of S minus I2 of S. So it will become R1 into I1 of S minus I2 of S, right? Plus 1 over C plus 1 over C into S into Q of S into S into Q of S equals to I of S, right? Here we don't have this S term, so it will become 1 by C into S followed by Q1 of S, means I1 of S minus I2 of S. That can be treated as a equation number capital A, right? How we are getting this capital A? By replacing this whole term S into Q according to the force voltage analogy. S into Q of S is nothing but what? I of S. The same terminology we need to use whenever we are dealing with this equation number 4, right? So as a result of doing this, equation number 4 will become what? Hereafter I will write this equation number 4. As you can see, it is 1 by C Q1 of S minus Q2 of S. S into Q of S is nothing but I of S. So it will become 1 over C into S followed by I1 of S minus I2 of S, right? Plus R1 into S times of Q1 of S minus Q2 of S. S into Q is nothing but R, right? So it will become plus R1 into I1 of S minus I2 of S, right? The coefficient of R1 is nothing but S times of Q1 of S minus Q2 of S. So it will become I1 of S minus I2 of S. Remaining term is nothing but what? Equals to the coefficient of L2 is S square times of Q2 of S, where S into Q of S is nothing but I of S. So it will become L2 times of S into I2 of S, right? Plus it is 1 over C2 into Q2 of S, right? So it will become 1 over, as we don't have this S term, 1 over C2 times of S into I2 of S, plus the coefficient for this R2 is S times of Q2 of S. S into Q of S is nothing but I of S. So which Q, here we are having Q number 2. So which current we need to consider? I number 2. So it will become plus R2 into I2 of S. This is nothing but what? Our equation number capital B. So from these two equations, equation number capital A and capital B, now we definitely can draw the final force voltage analogous circuit, right? Now the question arises how to draw this force voltage analogous circuit. So which is very simple. Carefully just try to see equation number capital A and capital B. Carefully just try to see the coefficients of each and every element. Here the coefficient of L1 is nothing but what? Which current we are having? S times of I1 of S, right? The coefficient of R1 is nothing but what? I1 minus I2 of S. The coefficient of it is 1 over which C we are having? 1 over C1. Here also 1 over C1 we are having. The coefficient of 1 over C1 is I1 of S minus I2 of S. Means through this L1, which current flows? I1. Through this L1, purely there will be a circulation of I1. As far as this R1 and C1 are concerned, through these two elements, which current flows? I1 minus of I2, right? When we are coming across to this equation number capital B, so at that time, similarly the coefficient of 1 over C1 is nothing but I1 minus I2, and the coefficient of R1 is means the same term we are having as compared to equation number capital A. To the right hand side of this, to the left hand side of this assignment operator in case of that subsequent equation capital P. But as far as this whole term is concerned, which is written to the right hand side of this assignment operator in case of equation number capital B, the coefficient of L2 is I2, the coefficient of C2 is I2, and the coefficient of R2 is also I2. Means through this L2 there will be a circulation of I2, through this C2 there will be a circulation of I2, and through this R2 there will be a circulation of I2. Means they are sharing the similar currents, right? So these three elements are connected in series form because these three elements sharing the similar current, so those are connected in series form. Which three elements? L2, C2 and R2, right? Similarly, as far as this L1 is concerned, so through that L1 which current flows? I1. So initially which statement we are having here? It is the force voltage analogy, right? So our force voltage analogous circuit will begin with this symbol belongs to this voltage, right? This positive plate and this is the negative plate, right? So the first component which we need to include, that is nothing but what? L1, right? This is nothing but what? L1. Through that L1 which current flows? Through that L1 there will be a circulation of I1, right? Now immediately after that we need to include these two components. Which two components? R1 and C1. So those are connected in this way. This is R1 and this is C1. Now one question arises in our mind, why these two components are connected in vertical arm? Because through this element there will be a circulation of I1 as well as I2. Because still we need to declare the right hand side of this assignment operator as far as equation number capital B is concerned, right? So to the right hand side of this assignment operator in this equation number capital B, which elements we are having? L2, we are having C2 and we are having R2, and the same current flow through this L2, C2 and R2. So those are connected in this way. So this will be the second loop of that network, belongs to I2. That is nothing but what? This is nothing but L2. This is nothing but what? C2, and this is nothing but R2, right? So through this first loop, this is R1, this is C1. Through this first loop there will be a circulation of I1, and through this second loop there will be a circulation of I2. That's why the coefficient of L2, C2 and R2, L2, C2 and R2, coefficient is what? I2. The coefficient of L1 is what here? The coefficient of L1 is I1, and the coefficient of R1 and C1 is nothing but I1 as well as I2. So this is the force voltage analogous network, right? So in this way, what we need to do, from that given mechanical system, we are supposed to draw the force voltage analogous circuit, right? Thank you.